Hi. Yeah, welcome this afternoon. Thanks for joining us. My name is Tom Asp. I'm with Power System Engineering, and I work with the Broadband group on working with the electric utilities across the country that are looking to get into the broadband business, and some of the times also for utilities that are looking to support other companies that are deploying fiber and expanding fiber in their territories. And one of the big questions always is, the make ready rules and regulations, and what are the types of cost and design that you really need to take a hard look at when looking at whether you're doing a fiber design yourself or looking at, supporting another carrier. And we have Mike is going to talk today about going through a lot of the different codes and different considerations that you want to consider as you're planning forward. Just to start, a little bit of a background about Power System Engineering. We're a full service consulting engineering firm that we have services ranging from rate studies, economic planning, business planning, but also kind of the full supporting range of the technical aspects of running an electric utility, including line design, substation design, and all those core engineering functions. And Mike Mezera heads our line design group, and we have Mike here to talk about, the considerations of make ready for broadband and the fiber optics. So from that, I'll turn the program over to Mike. One of the things, a little bit of a housekeeping, we are going to be kind of stopping periodically, taking questions, and you have instructions there of how to go through and submit a question, and during the breaks we'll go through and read out the questions and have Mike address the questions as they come up. And for that, kind of turn the next slide over to Mike here, and again, appreciate your attending this afternoon.
Well, thanks, Tom. I appreciate it. As Tom mentioned, my name is Mike Mezera, and I lead the line design group here at Power System Engineering. And we'll hopefully go through quite a number of things today regarding make ready. We'll look at some examples, but I kind of want to start with just touching base on really high level line design, which is what will be, that's the focus of my department and the focus of this presentation. We're really going to focus on overhead, aerial, cable and conductor design. There are definitely principles related to antenna attachments for broadband as well as underground, but really the engineering for make ready is a really high level for overhead construction. So we'll touch base on what that might consist of. Also today we're going to touch on NESC rules. My intention is not to have this be a lecture on the NESC or really go into the minutia of the rules that are covered there, but hopefully give you a high level overview of really what the rules are that need to be considered for any make ready attachments. Some that are overlooked, some that are not overlooked, but maybe not applied just correctly. And we'll dig into those in greater details. We'll also look at the factors to be reviewed when assessing make ready. Well, what kind of fiber are we going to use? Where on the pole is it going to be attached? What does that look like for loading or clearances that are related to those NESC rules? We'll touch on considerations for selecting fiber. I'll give you some details on what the different types of fiber will look like and how they may behave when they're in the air. But from a matter of planning or development of a broadband system, we're not going to get into those details. We'll also touch on considerations for installation and maintenance. Again, really how they feed back to those NESC rules that we'll touch on. The concepts that we're going to discuss today are, they're applicable to both an internal utility-owned broadband system or third-party attachments. I'll kind of reference both as we move through the presentation. And then as Tom said, Please add any questions that you may have. We'll try and take a couple short breaks to answer ones that come up. If they're related directly to the code, I do have a couple people working in the background. But again, our goal will be not to be a real specific minutia review of the NESC, but more the high-level topics. So the overhead view or high-level view of an overhead line design comes down to a number of components. If you were to break that down into major systems, you'd have your poles, cross arms, and insulators. Those are your support structures. That's what holds everything up in the air. So you're not on the ground with your conductors. We want an aerial system. There's rules for clearances above ground. These structures hold your conductors where they need to be. Not only do they hold the structures above ground, but they maintain separation between each cable or conductor on that structure. In the perfect world, lines are straight, point A to point B, but that's never really going to happen. So there's going to be turns, corners, stops and starts with your lines. At those points, guys and anchors are used to support any transverse longitudinal loads that the structures can't support themselves. And there are various rules that we'll look at, or rules and considerations that we'll look at for guys and anchors. The conductors and the cables are really the big consideration for any electrical system or communication system. This is what transports your medium from point A to point B. On the electric utility side, your conductors are transporting your electrons, transporting the electricity from the source to the load. The cables that we'll be talking about related to broadband, that's transmitting the signals that we're using. Obviously a big push for broadband these days, so we want to make sure that people are considering the interactions between the communication cables and the supply conductors, as well as how the loadings developed by those cables and conductors affect the poles, the structures, and the guys and anchors. Equipment and attachments. On any distribution system, you'll have equipment and attachments, transformers, lights, secondary cables, risers. All of these items have kind of modifications to NESC rules on clearance and may have strength factors that we need to look at. So we'll touch on those items as well. The big focus of this conversation will be more on the distribution side, where there are more equipment and attachments. I'll definitely be adding items related to transmission, but as we move through, you'll see that there are definitely a larger focus on the distribution side of things. The NESC, everything that we discussed today will be based on the 2017 NESC, which is the current NESC that's out there today, National Electrical Safety Code. Essentially, what the NESC covers is provisions and rules for safeguarding persons from hazards that arise from installation, operation, and maintenance of any conductors or equipment for overhead or underground electric supply and communication lines. It's developed by a number of basically committee members from utilities, from both electrical and communications utilities, railroad companies, independent contractors and consultants, labor unions, manufacturer associations, and government agencies. And really what it's there for is a set of provisions under specific situations that really are there to safeguard the public, safeguard the equipment, and safeguard the workers that are operating those systems. Everything from, again, electric utilities to communication utilities on overhead poles and underground systems are covered by the NESC. And so it's important to note that while rules are written such that the specific instances will lead you to an understanding of whether it's supply or communications, it's important to note that communication facilities need to follow the rules that are in the NESC. It's not just a matter of, well, that's not a supply conductor, it doesn't have high voltage, so it's safe. The NESC is there, again, to prevent basically issues with the public, workers, and equipment from anything that would come about in the environment in and around those utilities. For a third-party attachment or even an added internal in-house broadband attachment, if the utility company pole and their supply lines themselves meet the NESC, it's not a guarantee that the new attachment will meet the NESC, so everything needs to be evaluated, and that leads us to this make-ready discussion. So jumping right into the NESC rules that I'll be covering, essentially what you'll see on the next number of slides is a rule given, and then we'll kind of touch base on what each of those will cover. Anytime it's pulled directly from the code book, I'll have a little icon showing the cover of the code, and hopefully we can work through those items and see how they apply to each situation. So to start with, the NESC rules that are most often considered for broadband make-ready, the big number one would be NESC Rule 235C1B, which basically lays out the separation between a supply system and a communication line. And basically, it directs you to this table, Table 235-5, which, if you are familiar with it, lays out the distances between cables and conductors attached to the same pole. Essentially, what most people are familiar with is this 40-inch rule. So looking at the basically conductors or cables at the lower level, you see communication conductors on the left side of the table. Conductors and cables usually at the upper level, you see supply cables, neutrals, and so on. And if you have a communication cable located in the supply space, you see the rule of 40 inches of separation required. So very typical that people will say 40 inches is required at the pole. We'll look at some additional instances of where that comes from and what that means, as well as some exceptions to that rule. But in my experience, that is the number one rule that's most often considered when making an attachment for a communications line, is that we need to have 40 inches between that communications line and the neutral. And other rules that are considered, that's about it. Well, I would say that this is kind of a mixed bag. Some people do a very good job of really knowing in and out what needs to be done for attachments, whether it's, again, an in-house attachment or a third-party attachment. But in my experience, I definitely see that once you go beyond that 40-inch rule, it's really lacking in what people either understand about the code, apply to their own systems, or try to apply to other systems if they're a third-party attacher. While looking at rules or a new line attachment, consideration is given to above ground clearance, but there's a lot of misinterpretation that happens with those rules. Consideration is also given to structure strength, but the way that the lines are laid out may not necessarily meet code requirements or industry best practices. And we'll get into that in greater detail. So from the perspective of NESC, there's really a lot of rules that need to be considered for any attachment, whether it's an in-house broadband or a third-party attachment. And I'd even go to say that this isn't necessarily an exhaustive list, but these are the big ones that really need to be considered for any sort of attachment. NESC Rule 232, again, this is vertical clearance above ground. Sometimes it's covered well, sometimes there's some misinterpretation that hopefully we can clear up some of those items today. NESC Rule 235C1B, again, the clearance at the pole, 40 inches. Again, that's widely known, widely accepted. There are caveats to that rule, like I mentioned, and exceptions that may may affect those clearances, but for the most part, that rule is covered pretty well. SAG-related clearances are a big sticking point that impact that 40-inch rule at the pole, and there's quite a lot of information that needs to be reviewed for those clearances, and it's one that I see overlooked time and time again. Rules 235C4 and 238E related to the communication worker safety zone really set the stage for a lot of the other clearance rules. It brings us back to that 40-inch separation at the pole, but also is, I mean, it's the reason why we have these other rules within the code, and that's to keep the workers that are authorized to work in the communication space, and those are authorized to work in the supply space up into the supply space. So again, that's very, very important, and it kind of comes back and forth in a number of the rules that we'll be looking at in greater detail. 238-1 will have some exceptions to clearance requirements for equipment, and then similarly in 238C and D, clearances to luminaries. We'll look at clearances to risers in 239G1. And then, as I mentioned, the strength value, or the strength rules laid out in sections 24, 25, and 26, they're usually handled okay, but again, there are some items that are done that I've seen that may not necessarily meet code, or more likely they don't necessarily meet industry best practices. So I thought maybe I'd just take a quick break right here just to see if there's any questions before we move forward.
Yeah, we do have a couple of questions here, Mike. Excuse me. And the first one is one I could actually answer. And the question is this presentation being recorded? And yes, the presentation is being recorded, and we'll be posting that on our website shortly after onto that. So the second question actually is technical, so I'll have to have you answer that one. And that one is that one that says, how do ground clearances apply in a pedestrian-only location?
Sure. Yeah, absolutely. We will get into that in a little bit greater detail in a couple slides here, but essentially what I've seen, and I guess I'll give an example for that, is a lot of times there's a table 235 in section 235 that deals with these clearances to ground, or sorry, 232 that deals with these clearances to ground. For most communication cables, you'll see the rule is around, I believe, 15.5 feet. Again, I hopefully we won't do too many direct numbers without the code book right in front of me. But also there are caveats to that where pedestrian-only situations, the clearance can be reduced to 9.5 feet for communications cables. And really what I like to see, or what I do see, is that a lot of third-party attachers will try and use that rule across the board at a lot of places, even if it's not necessarily a pedestrian-only location. Pedestrian-only locations, really as defined in the NESC, I mean, they're areas that are neither anticipating or expecting vehicles to be driven, or there are, I guess, caveats to the rule where it's riders on horseback. Really, whenever I would like to look at a clearance review related to a pedestrian-only situation, I'm really looking for an area that it's either there's a permanent physical terrain that is causing no vehicle situations, or it's not something that's going to be altered in the near term. The designer doesn't necessarily have to think of every possible situation that could ever happen, but to not really look at things that could happen and just going with a reduced clearance could really bring about issues in the future. One example I guess I would point to would be a line that's kind of outside the road right away, maybe adjacent to a ditch. and then a cultivated field. You might be outside the road right away, so you would say, well, I don't expect truck traffic to be here. There's a ditch, or I'm not necessarily right on the edge of the field. But if there's a gray area of, well, we could have a vehicle here, or maybe they could add a driveway, a new field approach, having additional clearance in these situations will save headaches and save costs down the road. Other areas like dense backyards with fences that have been in place for a long time, those areas that maybe the exception can be made and you can go with a reduced clearance. If the only vehicle that's going to be back there is maybe a riding lawnmower. But areas that are potentially adjacent to driveways, you could be backing in large vehicles, or maybe areas where you'd want to go with a higher clearance. So in summary, I mean, I guess what I'm trying to say, and hopefully answering the question, is whenever those reduced clearances come into play, take an extra level of scrutiny before going with the bare minimum. The NESC is already kind of minimum values, so using exceptions to bring those values down, if the solution to maintain the larger values is not extremely costly, it's just a potential can of worms for liability if something were to get into those lines.
Yeah, I got a follow-up question to that, Mike. And one is that on these clearances that you're talking about, is this at any time or are they under certain conditions? And I think where the 15 and 9 feet, are they, anytime, or are they under certain SAG conditions?
Yeah, absolutely. And actually, I'm going to go forward to the next slide, and hopefully this will help answer that question. So from 232, vertical clearances, either this 15.5 or this 9.5 or any of the other clearance values that are laid out in the rule, they're really based on the worst case SAG. So the vertical clearances apply under the following conditions, whichever produces the largest final SAG. So I'll use the terms synonymously, but largest final SAG or worst case SAG, it's whenever the conductor is closest to the ground. And it's under these conditions that are listed here, either 120 degrees Fahrenheit, no wind displacement, the maximum design temperature, if greater than 120 degrees Fahrenheit, no wind displacement, or 32 degrees Fahrenheit, no wind displacement with radial ice as specified in table 231. And I believe I have that table here. So the ice loading is, it's based on kind of the region that, or I should call it the district or the zone that the line is being built in. So zones 1, 2, and 3 represented here are similar to the heavy, medium, and light zones in other portions of the NESC. And then they are analogous to the table on the right side there that shows the amount of ice necessary for loading. So in zone 1 or your heavy loading zone, you have to account for a ½ inch of ice on your conductors. In zone 2 or the medium loading zone, kind of in the middle and western states, a ½ inch of ice, and then in zone 3, 0 ice. And what that means is your worst case SAG may be at different conditions. When there's more ice, depending on the type of conductor and the SAG characteristics, which we'll get into later in the presentation, but generally you'll have more SAG under an ice conductor than a hot conductor. But if there is no ice requirement, such as in zone 3, the temperature is going to control your worst case SAG. So bear that in mind, that during design and during the design process, take a look at what zone you are located in. If you're in zone 1, zone 2, take special care to see what that ice does to your conductors or your cables, and how they sag out, again, when measuring those clearances that are related to the rules. NESC table 235-5 is another rule that's that affects clearances. Vertical clearance may be reduced to 30 inches for supply neutrals, meeting Rule 231E, and that's basically effectively grounded neutrals that are associated with circuits up to 22 kV, and then fiber on effectively grounded messenger or entirely dielectric fiber. So by this rule, or the footnote in this rule, you can have a minimum of 30-inch separation between the neutral and the top communications conductor in some cases. But bear in mind, sometimes you're going to use a secondary conductor as your system neutral, or well, in this picture, as the neutral stops, the secondary continues on, so it is that neutral. You need 40 inches from the secondary because it does not meet the other provisions of that rule. Again, bear in mind that there are exceptions to the rules, but make sure that you're covering the proper situation whenever making those exceptions. An additional rule that impacts the clearance at the pole and may require greater than 40 inches is seg-related clearances, which come up in 235C2B. This is the abridged version of the rule. I think it's on a number of pages in the code book. But essentially what it boils down to is there are several conditions at which clearance in span needs to be maintained at a certain level. And in order to maintain that separation in span, you may have to increase the clearance at the pole itself. So per the rule, basically conductors below 50 kV, 75% of the clearance that is required in span, or 75% of the clearance required by 235-5, or clearance at the pole, is required in span. So if you have a 40-inch separation required at the pole, you'll need a 30-inch separation required in span. For conductors or circuits above 50 kV, there's a base value depending on what that voltage is, and then an adder for additional kilovolts above 50 kV. The clearances that are described in those situations kind of come back to this worst case situation. We want to look at this when the two conductors are closest together. So it's either the upper conductor is hot, either at that 120 case or the highest operating temperature, and then your lower conductor cable is at ambient temperature, or the upper conductor is at 32 degrees and iced, and the lower conductor is at 32 degrees with no ice. So these two cases generally bring your conductors closest together, conductors and cables closest together, and so that is when we want to be reviewing this rule. Also within this rule, basically adjustments to seg used to meet clearances should not exceed conductor strength limitations. So if the plan is to, instead of basically spreading out your attachments at the pole, you're going to either tighten or loosen your conductors to change the segs, it has to be reviewed so that the tension limitations set out in section 26 are adhered to. An additional rule for spans longer than 150 feet, vertical clearances at the structure shall be adjusted so no open supply conductor between 750 volts and 50 kV at 60 degrees final sag shall be lower than in the span than a straight line joining the points of the support of the highest communication conductor. And I have an illustration that kind of walks through these items. So the basic provision of the rule is that 75% of the in-span required clearance is 75% of the at-pole clearance. So again, if we have 40 inches at the pole, then we need 30 inches in span. The conditions that has to be met at would be the supply at 120 degrees Fahrenheit or its highest operating temperature above 120 degrees Fahrenheit, and then the communications conductor or cable at ambient. So maybe you have your supply at 120 degrees on a hot day, and then your ambient temperature is maybe 90 degrees that causes your supply to run at 120. So the cable would have to have the sag of a 90-degree day versus a 120-degree case for the supply and still maintain that 30 inches. Similarly, with the ice case, it's your upper conductor iced and your lower conductor ambient without ice. This may be, can generally be a sticking point for like an ADSS cable, which we'll look at in a little bit greater detail. But those types of conductor or cables don't sag very much under temperature. So the line that they draw from sag perspective is relatively flat, whereas the supply conductor may have several feet of sag under an ice case. We'll touch on this again as well, but the ADSS may sag a lot under ice compared to temperature as well. So keep that in mind when looking at ground clearances. Finally, this 150-foot span rule, with the supply conductors at 60 degrees final sag, they cannot be lower than a straight line between the supports of the communication attachment. This doesn't apply to neutral conductors, so you can see in the illustration here that they are below, but that 40-inch minimum may need to be increased to maintain that separation. And important to take that into consideration with any terrain that you might be dealing with as well. Again, coming back to the communication worker safety zone, this is, again, it's kind of the real paramount item for this, and it's all ties back to safety for the line workers that are working on these systems. If they're not trained for the supply space, they should be in the communication space. And the clearances that are set up in 235 and 238 make up this communication worker safety zone. And what it comes down to is there's a supply space generally at the top of the pole, a communication worker safety zone below that, and then a communication space below the communication worker safety zone. Per the NESC, there should be no attachments within that communication worker safety zone other than by specific rules that allow for certain attachments. And what that is, I mean, the goal of that separation with no attachments, it allows for a clear demarcation, a visual separation between where the communication space ends and where the supply space begins. So workers that are trained for the communication space may not have the knowledge necessary to work in the supply space safely. They know that there's this gap on the pole, the communication worker safety zone. Don't approach anything above that location. So how do we determine the communication worker safety zone? We talked about a couple kind of variations to the attachment point on the pole as it compares to the supply space. Basically on the left here we have our attachment located in the communication space, 40 inches below our neutral, or we have the option of locating in the supply space 16 inches below the neutral. I guess I will point out that if we're looking at a point that's 16 inches below the neutral, the sag and clearances, in my opinion, take on a higher degree of scrutiny because there are exceptions for separation in span when we're attached 16 inches apart at the pole, but avoiding kind of conductors coming together or cables coming together, which could cause abrasion on your various cables, could be a risk. So I try to take a close look at anything that's located in the supply space. So we've established we have attachment. We are the power utility, and we are installing our broadband on the pole, and we're going to make a decision on where our attachment goes relative to other attachments in this situation. When we attach in the communication space, new attachments or third-party attachments should be 12 inches below our attachment, unless by specific agreement between the parties. I've seen in certain situations where you have multiple attachers on the pole, it's good to have a consistent 12-inch separation and maintain sags such that you can maintain that separation, versus the alternative being we have 12 inches between these attachments, 16 inches between these attachments, 24 inches between these attachments. What it does is it eats up a lot of the pole, and so if there are multiple attachers on there, certain attachers are not getting, I guess, the true benefit of that space on the pole. And it's just going to cause more expense later on to try and determine who caused a violation, who caused a make-ready expense if those poles need to be adjusted. Now, when attaching in the supply space, I guess the question becomes, well, does the same 12 inches apply for a third-party attacher below us, or do they need to be 40 inches below us? And the answer to that question is they need to be 40 inches below. Any cable or conductor that is established in the supply space reestablishes that 40-inch communication worker safety zone. So any additional attachments beyond that that are supposed to be in the communication space need to have that clear demarcation of 40 inches from any cable or conductor in the supply space. A question that I've had come up previously is our poles in the field have a third-party attachment, and now we want to add our own broadband to these poles. Can we use the exception to attach at 30 inches below our neutral and have the communications attacher remain at their 40-inch location, or do they need to be adjusted? And in this case, the added attachment in the supply space reestablishes that communication worker safety zone. So any existing attachment would need to be adjusted down the pole, or that pole would need to be adjusted so there's more clearance available on the structure. So from the perspective of clearance to between equipment and conductors, Table 238-1 can be used. Essentially, non-current carrying parts of supply equipment that are effectively grounded can have reduced clearance down to 30 inches. It's important to consider what you're looking at when you're reducing your clearances. So if you're reducing spacing to less than 40 inches, distinguish which parts are energized and which parts are grounded. So here we have kind of a service location with a transformer and a secondary tap or service drop. The neutral drip loop or the bottom of the transformer could have a 30-inch clearance, but any of the live cables in that service conductor would require that 40-inch separation. So it's important to note exactly what you're looking at whenever you have a situation like this. Similarly, for luminaires or light structures that are in the on the poles, security lights, street lights, what have you. These have their own specific clearances given in the table shown here, with exceptions to the rule. Essentially, the lowest point of a drip loop entering a luminaire shall be not less than 12 inches above the highest communication cables. This can be reduced further by an additional exception, but basically the cables need to be covered properly so that in order for that rule to take effect. But what that looks like visually is we have an attachment here with a street light. We have a duplex attachment, which is coming from our transformer source to feed the street light. We have the bracket at which that light is attached, and we have a drip loop coming out of the bottom of that, or coming into the bottom of that light. Again, the energized conductor at the duplex attachment will require that 40-inch separation to a communications attachment. The bottom of the bracket can be reduced to 20 inches, assuming it's effectively grounded, and the drip loop that's entering the bracket can be reduced to 12 inches or further by additional exception. Again, take note that when multiple clearances apply, the greatest of those clearances is the controlling factor. So if for some reason the duplex attachment was lower on the pole, closer to the base of the bracket, you still need 40 inches from the bracket, or from the duplex to your communications attachment, even if you have 20 inches to where that luminaire bracket is. There are also clearance requirements for risers. And a riser is a location where your supply conductor essentially transitions from overhead to underground. So at those locations, your conductors they're going to be running through the communications space. And so guards need to be put in place to protect, again, both the workers and the equipment from any issues that may arise in that space. So essentially 40 inches is required from the top of the guard or conduit between until the highest communications attachment, or I should say, and in addition to that guard may be removed 6 feet below the lowest communications attachment. Again, modified by other exceptions, but 40 inches between, again, the top of the conduit essentially is now the new bottom of that supply space and the new top of the communication worker safety zone. Again, depending on how that riser is positioned in relation to other attachments on the pole, be it the neutral or other risers or other equipment, transformers in the case of a secondary attachment, the greatest requirement for clearance is the one that will control the attachment point of communication cables. An exception to the rule, basically the conduit or covering may be omitted from a neutral conductors meeting 230E1, supply cables meeting 230C1A, and jacketed multiple conductor supply cables of 0 to 750 volts where such conductors or cables are not in the climbing space. The cables referenced in 230C1A, it basically involves a shielded cable, which is not typical for most riser locations in today's cable. You're generally dealing with a concentric neutral. And really to the point, unless you're 100% certain exactly what kind of cable is being run through this riser, it's best to maintain that 40 inches rather than take the risk of something going wrong and having a worker in a place where they don't belong, leading to a liability situation. Items to consider related to sections 24, 25, 26. These are the strength rules. Essentially, the grades of construction for any structure need to be based on the highest grade of the conductors on that structure. So if you have a transmission structure with transmission conductors and you're going to add an attachment, the structure needs to be analyzed under grade B load factors, which would be required for that transmission circuit. Loads due to ice, wind, and conductor tension should be multiplied by load factors based on the required grade of construction, is part of section 25. So the basically there's overload factors, and then in the next point, the strength factors from section 26 that get applied to the entire, basically load factors get applied to ice and wind loads, strength factors get applied to your structures. The combination of the two creates a safety factor for any attachment to those structures. And the goal is to basically create a system that will withstand ice and wind cases with a safety buffer for material deterioration, construction tolerances, what have you. So those items need to be taken into consideration for both supply attachments and communications attachments. Conductor cable strength limitations we touched on, usually not a huge sticking point for attachments unless the spans are very long. But the consideration should be that if you're in a situation where you need to increase the tension of your cable to accommodate sag, for example, there are certain limitations within the NESC that should not be exceeded under certain load cases, and to avoid those, or to basically ignore those, could lead to damage to the conductor. Again, the overloading of your conductors leads to basically tension limitations, and the more tension you have on your structure, pulling on your structures, the more there's going to be pulling on your supports, like the anchors in this particular situation, where it looks like there's a failure from the anchor, possibly from ice or wind loading that was not properly accounted for. It's been some time since we took a question break, so maybe see if Tom, have any other ones come up?
Yeah, I do have a couple of questions here. Again, the first one here, can clearances be reduced if the communication cable is supported by a standoff bracket?
Yes. Well, I should say no. Yes, I understand the question, but the short answer is no. I've seen this. What this comes down to is basically, it's usually you see this in a third-party situation where maybe the attacher can't quite get 40 inches at the pole and still maintain ground clearance, and you'll see a small fiberglass bracket off the side of the pole to move that that cable away from the neutral conductor. And so really that's not a legitimate solution. The clearance values that are laid out in the NESC for separation at the pole, they're vertical clearances. They're not diagonal clearances. So to just move the cable to the side in order to increase the separation between the two doesn't meet the intent of the rule. I like to think of it as basically the supply space. The bottom of the supply space is a plane that extends out from the pole into the span and around the pole. And the same thing with the communication space. It's a plane. It's not just a point on that structure. So the clearances that are required should be the vertical line between those two planes in and around that structure.
Okay. Then you have one more, and that's are there rules for minimum separation of anchors?
I don't believe there are specific NESC rules for separation of anchors. I guess one situation that comes to mind is when you have multiple attachers on a pole. You have in an angle structure, the communications attacher may need to add a guy to support that angle. If the supply utility does not allow third parties to attach to their anchors, they need to add a new anchor. And it's good utility practice to allow separation between those anchors in order to basically have them allow for their develop their full holding potential. Again, I don't think there's a rule for this, but An example that comes to mind is RUS bulletin that recommends 5 feet between anchors in soil and 2 feet in solid rock. I personally like to see 6 feet. It's just easier from a staking perspective, but keeping that separation when you need to add multiple anchors helps with the holding power of those structures. And I guess that kind of leads me to one other point is just because the communications attacher is adding a guy in an anchor doesn't necessarily mean the supply utility is has sufficient strength in their anchor. So make ready could be an existing condition for a situation like that, and both should be evaluated, the existing and the proposed. Any other questions, Tom?
No, that's all the questions so far.
Okay. Additional things that should not be overlooked when it comes to attachments on the NESC. Grounding and bonding are key to a lot of the rules and specific to how we look at where the clearances are and how they're reduced. Be mindful of transitions between supply and communication space. So for owners that operate in the supply space, you can enter the communication space at certain locations in the system, but those transitions should be really made at the pole versus from one pole to the other in span transition, just so it's clear where that demarcation is. I touched on the next point, but separation at the pole should not be less than 12 inches or 4 inches in span for between communications attachments in the communication space. Separation can be reduced to 12 inches for the final span to a meter point or to a service point, or let's say you have a meter pole, the span to that pole and the attachments at that pole may be 12 inches as long as proper separation is maintained at the transformer pole or any intermediate poles. And again, when in doubt for a rule or an exception to the rule, always err on the side of caution or on the conservative side. There are many factors to consider for assessing make ready. Really, what information do you have up front? We want to know what is being attached, where on the pole it's being attached. Is it a ADSS? Is it a fiber lashed messenger? How is that going to sag? What are the worst case sags? What are the worst case clearances? What do we know about the existing plant that's out there? Do we have paper staking sheets from the 60s available, or do we have a good GIS system where we know exactly what poles, what heights and classes they are? All that information available can expedite the process. Again, the condition of the existing plant will impact our make ready as well. Long spans on short poles are pretty common for old construction or legacy construction. So if your supply space is already at the bottom of the clearance allowances, it's going to be hard to attach a new cable without some significant make ready. Additionally, if the poles are very old, I mean the strength may be out of those structures. You may have more danger flag poles than on a new line. Existing attachments can also complicate the process. Again, this can come down to, well, where are we going to attach on the pole? What other spaces are available? Was a good assessment of make ready conducted for the existing attachment, or do we have existing violations that weren't caught up front? And then who's going to pay for those issues now that it's years down the road? And then who is going to perform the assessment is also key. So for utilities deploying their own broadband, you can follow your in-house standards and have in-house crews determine basically what's going to be where and how it's going to look. If a third party is coming in, a lot of times you're going to need scrutiny to make sure that they are in fact following the rules and making sure that the that both the make-ready assessment and then later the attachment is done to your specifications for a safe situation. The next slide I have here kind of deals with expectations versus reality for make-ready, and these are kind of things that what I've seen are call it good or bad for make-ready assessments. When talking with utilities, a lot of times they say, well, we need 40 inches at the pole, and the clearance looks good. I mean, it looks good today, but we've talked about how we need to make sure we're looking at our worst case clearances. And then again, there are instances where 40 inches separation at the pole is not adequate. So on the right side here, we've got other drivers that can increase make-ready costs. Again, inaccurate records or assessment data. So if we don't know exactly what's out there, the process for determining what make-ready is needed can be a lengthy process, really involved engineering process, and it can make things more difficult. Again, if you don't know exactly what's out there, you're not going to know exactly what needs to be changed or modified to accommodate a new attachment. The clearances laid out that we've discussed, well, is it worst case? Is it when the conductors are closest together? Do I need more than 40 inches at the pole? If the spans are longer, I mean, you may run into situations where this is more prevalent. Again, existing violations. If you don't know exactly what's out there, who's going to pay for it, or who's going to be footing the bill for correcting those issues? And then pole changeouts. What I'm referring to here is a lot of times I'm told that, oh, well, if we just move the neutral up here, or tighten the secondary here, or extend the riser a few inches, we should be good. When really the pole changeouts are going to be your costly factors. So whenever you have a situation where you can't meet your other clearances with just an adjustment at the pole, a changeout is the next step, and those are going to be your costly fees. So expected make-ready costs. Really, I've seen this very prevalent. Utilities going through a make-ready procedure, or third-party attachers saying what they're used to seeing, maybe 5 or 10%. 1 or 2 poles per mile being changed out, a couple of poles per mile, a handful of adjustments here and there. If all of the factors are reviewed with the proper scrutiny, basically an experience from what PSE has seen in numerous attachment reviews from different utilities, different types of attachers, different regions, it's pretty uncommon to see less than 15% make-ready, be it adjustments at the pole or pole changeouts, and upwards of 50, 60, 65%. It's not unheard of. This can account for, again, those clearance issues, usually more prevalent on the distribution side. Strength issues can be more prevalent on the transmission side, especially if you have really long spans on older structures that you're trying to retrofit. So moving into kind of fiber selection, 2 big types of fiber that I see go out for broadband applications on both transmission and distribution systems are fiber with a messenger, whether it's a lash to a separate messenger, or like a figure-8 style that's shown here, where the 2 are jacketed together, or an all-dielectric self-supporting, or an ADSS. Both of these obviously carry communication signals from point A to point B. They have different characteristics for how they're installed, the costs associated with their installation, the requirements for NESC clearances and separation, and those will affect your make-ready costs. Kind of a general overview of the 2 side by side. the lashed fiber or even the figure 8 fiber relies on a messenger for strength, whereas the ADSS has an internal strength member. The lashed has 2 cables, the messenger and the fiber itself, whereas the ADSS is just the cable by itself. Whenever you have that metallic messenger, it must be bonded with following the correct grounding rules. And if you're looking for reductions in clearances, again, everything needs to be bonded together. The ADSS is all dielectric. Lashed conductors sag under temperature and ice loads comparable to conductors. So depending on the size of the cable and conductor you're looking at and the zone that you're in, ice may be a factor or temperature may be a factor. Whereas ADSS has minimal sag under temperature, as I mentioned before, and considerable sag under ice load. So if those ADSS get iced, there's likely to be considerable sag. And we'll look at what those numbers look like here in a couple slides. Generally what I've seen is installation costs for lashed fiber are typically a bit higher. Basically, I mean, there's 2 operations to install the cable. You have to pull your messenger, and then you have to lash the fiber to it. Whereas the ADSS, it's a single cable installation, but the cable itself is generally a higher cost. So when determining the balance of how a utility will deploy their broadband, taking those items into account is definitely important. More on the transmission side, again, a fiber lashed to messenger or an ADSS cable can be applied to a transmission structure. Optical ground wire or OPGW is definitely a viable option as well, especially for new construction. And basically what it comes down to is these OPGW cables that contain fiber can be sized and sagged similarly to your typical shield wire. They may be somewhat bigger in diameter depending on the number of fibers you have in the cable, but generally they're pretty close together from a sag and strength perspective as well. When using this, they act as the lightning protection, and I kind of touched on this, but retrofitting for old transmission lines can be costly if the line can't be taken out of service. And it all kind of depends on the original design of that conductor. Now again, ADSS cables can be attached, or messenger cables can be attached to transmission lines. Again, there are specific clearances that are related to the voltage of those lines. And also something that shouldn't be overlooked is space potential. If you're looking at an ADSS, you can get closer to the transmission conductors, but there are limitations before you have issues with the jacket tracking or causing damage. Why don't we take just a quick break if there's any questions?
Yeah, I do have one question. And do you have a strong preference for fiber in the static versus a separate fiber cable?
When it comes to I guess a transmission situation, my opinion is that having that fiber, the OPGW is a benefit. Again, you can have similar characteristics to a shield wire, so the loading of the structures is not necessarily greatly increased. The cost differential between a standard steel static wire and OPGW is quite a bit, but making up that cost from having an ADSS lower on the pole or a fiber lashed to messenger lower on the pole may balance that out. It depends on how it's going to be installed. Is it a new installation or is it a retrofit? But overall, I would say when it comes to transmission, OPGW would generally be my preference. One other point, I mean, the loading of a single conductor at the top of the pole is still going to be less than having just a plain static wire and then an additional attachment lower on the pole. So if you are retrofitting, you may have more make ready related to strength from adding a second conductor versus changing out the shield wire with OPGW.
Yeah, no more questions right now.
Moving into some considerations for installation and maintenance. Again, we kind of go back to this communication worker safety zone. Who is going to be installing the cable? Who is going to be maintaining it? And if you have the proper spacing on the pole, there's clear demarcation for where the communication zone ends and the supply zone ends. Safety is a big factor for that. When determining where you're going to attach, it comes back to who's going to be working on the pole. If you have it in the supply space, you're going to want to have line workers that are trained, equipped, and authorized to work in the supply space, operating the facilities. If you have it in the communication space, you may be able to have additional line workers working on the facilities that aren't necessarily certified for supply. Again, it comes down to safety and then again internal preferences for from that perspective. Sag and tension is a huge consideration for any fiber installation. You have obviously the installation piece of it, separation at the pole, and then separation in span is all going to be based on sag and tension. There's a number of software systems out there that can be used to review sag and tension situations for different types of cable. Generally what I see is sag 10 is used prevalently for conductors, and then CommScope SpanMaster is used prevalently for fiber, particularly fiber lashed to a messenger. And then the comment that always comes up, which I have here, is we just sag the fiber to match the neutral. And what my hope is that won't be that plan won't continue to proliferate in the future, because what it comes down to is what condition is the neutral at when the fiber is sagged to match. I have here just a printout of a sag 10 data sheet for a 336 conductor on a 250 foot span. So let's say we have a 3-phase feeder with 336 conductor. The conductor itself, it's metal. There's steel, there's aluminum in the conductor. It changes length, changes sag under heat, under ice load. So you can see from the table there's quite a bit of information. Even if you're not familiar with this type of printout, basically what it shows is that at cold temperatures the conductor sags about a foot, and then at hot temperatures it sags upwards of 5 feet. So let's say we're sagging in a fiber to match our neutral for this line. Given two situations, if we are installing the fiber on a new 3-phase line, we can look at the initial tension. If we're installing it on an existing line, maybe we're sagging it to final tension. If we're matching it at somewhat new or somewhat old line, maybe we don't know exactly where that conductor is, and then it's hard to say where our final clearances will end up. But looking at the two situations I've highlighted here, if we were to match the sag on a cold day on a new line, there's just under 2 feet of sag in that neutral. If we were to match the sag of an existing line on a hot day, there's over 4 feet of sag. So your fiber will be sagged at either 2 feet or 4 feet at that specific temperature when the fiber is brand new, whether the conductor is new or old. I've got here just the screenshots of what the CommScope would look like for these. We'll look at it a little bit closer so it's so the details can come out. But basically, the inputs here are showing the 1.91 feet of sag at 30 degrees, and then on the second page, 4.32 feet at 90 degrees final sag. If we look at the sag characteristics for what we need to look at for our NESC clearances, you can see there's a big difference. So when we match the fiber to the 30 degrees initial sag, under a 32 degrees with ice case, there's 4.89 feet of sag. When we match that same cable at 90 degrees final sag, there's 6.11 feet of sag. So over a foot, about a foot and a half additional sag between those two conditions. The bottom line on these tables is just the 32 degrees no ice case. So for the one on the left, the 30 degree case, there's just under 2 feet of sag. For the one on the right, there's a little over 3.5 feet of sag. So based on these conditions, well, we just matched it to sag, sag the neutral. It doesn't necessarily mean that these values are going to match the neutral at other conditions that are necessary for construction or for make-ready clearances. If you're matching it at a cold situation, the question really becomes, is the separation in the span still going to work out? If you're matching it at a hot condition, the question is the ground clearance still going to be adequate under worst case sag conditions? So this example is based on a fiber lashed messenger. We can look at the ice loading considerations for an ADSS cable as well. I have here just a general data sheet for an ADSS cable. If we look at the sag recommendations for, I believe these values are for 144 count fiber in the various loading zones. Basically, if you have 1% installation sag at a 300 foot span or 3 feet of sag at installation, your ice value is going to be significantly higher for the loading zones. So again, for the heavy loading zone, it's almost 10 feet of sag in an ADSS fiber. So really the consideration that needs to be had here is, do I have proper separations in the span under temperature conditions where there's minimal sag, and do I have proper clearances to ground under these more significant ice loading cases where applicable? So definitely something to take into consideration. ADSS cable can be modified so that the strength members are increased or decreased to basically match more closely to conductors, metallic conductors, but it all comes at a cost. Really what it comes down to is increasing the strength member and reducing the installation sag will bring about a system that's more likely or more akin to a metallic messenger, but there's additional cost that's associated with that strength member. And that kind of brings us to the wrap-up point. Really, the goal of this webinar and previous webinars or upcoming webinars is to talk about various facets of the broadband process map. The items that we really touched on today are from the design parameters to pre-attachment and then make-ready, and somewhat to the post-attachment field. But there's more to it. Routing, planning, feasibility would be more up Tom's alley. But the items that hopefully you can walk away from today are that definitely need to be putting some scrutiny and consideration to what conductor or what cable we're going to be putting out there, where it's going to be attached, and what those sag conditions are going to be. Then performing a good assessment of the system, of the existing, of the proposed, to make sure that everything is in line with those requirements. Adjusting attachments, doing make ready, replacing poles to accommodate your broadband, and then doing a post attachment assessment is often a good step that can be misplaced, just to verify that things do line in with how they were expected, and then everything is up to spec the way you had planned. So with that, I think that's all we had. Tom, I don't know if there's any additional questions, or looks like we're a little bit over time. Hopefully, I'm happy to answer questions, obviously, but.
Yeah, there's just one more here, and it just says, do you recommend attaching in the supply or communication space?
The answer is kind of, it depends.
Yep.
I mean, I'd like to see the supply space really kind of gives you more protection for the different facilities. It keeps everything separated from each other. You don't have to worry about the items like abrasion or who's going to be installing and maintaining the lines from the perspective of, are they certified to be in the supply space. So attaching in the supply space can definitely have its benefits. It uses less of the pole. You can distinguish which communications facilities are the utilities, but it can cause more issues depending on how additional attachments are made to those structures. So I would lean towards attaching in the communication space myself, but again, there's lots to consider for making those determinations.
Okay, that's all the questions that we have here. So.
Okay, well, excellent. Again, I appreciate everyone attending today. Sorry we went over time a little bit, but hopefully you gained some good knowledge from this presentation. And if there's any questions that you have offline, we're happy to answer them. Tom and my contact information is provided, and we will follow up if there's additional questions. So thank you very much.